and we've progressed up to social network analysis, which is a specialization of network analysis. And the approach that we're going to use, we're going to shift here. It's going to be exclusively visual, at least for today, and makes use of this package, this R package, igraph. There are a number of visualization packages in R, but I really have found that igraph seems to be the most flexible in terms of what you can do and the ease with which you can do it. And that might not surprise you if you look at the documentation which you have. This thing's a monstrosity. The package is 300 and the documentation is over 300 pages long. The only other R package that I've seen of this magnitude substance is William Ravel's Psych package. So this thing's a monster. I mean, it wasn't made overnight. It's used in a lot of very interesting and unique applications. For example, the SemPlot package that supports the drawing of estimated path models for just about any covariance-based class of objects that you have in R, Sem, Lavon, as well as any sort of linear model. It was developed in igraph, and it's really excellent. It's the plots that it turns out that show the fits and do all kinds of interesting things was based on igraph. So I think you'll like this. And just for my own personal comment, I've been looking for the right plotting package to enhance Dean and my PLS GUI application on the visual side, and this is it as far as I'm concerned. So we're going to start off today. I'm trying to move it along. I do have the script from last week, and I was thinking about redoing the sampling section because we kind of rushed through it. But let's see how far we get here. I want to move along and cover all the topics that we originally had planned. So let's first start with a tutorial on igraph, a really basic tutorial. It does so many things. And it's at its most basic level, it is not R-based. It has been ported into R, but if you Google it a couple of times, you can find I believe it's on a .org site, and there's a standalone executable, I believe, that you can download into a Windows environment and use it without using R. But it creates directed and undirected graphs. Now, a graph at its simplest level is just a collection of nodes and links, and the links are called edges. Directed means that the links have arrows, go in one direction or the other, and undirected means that they don't. So let's take a look. If you have never used igraph before, of course, you're going to have to install it, and then, of course, load it as you do anything else. So graphs are networks. They consist of elements or objects at the most basic level, nodes and edges. So here, let's create one just to demonstrate what we're talking about. And so we use the graph function in igraph, and we execute this command. And in the tutorials that I have encountered, they like to build up these graphs with a series of statements and then plot them. I find it more instructive to actually plot it anytime you make a change. I know that helps me understand what the last statement did rather than running a whole bunch of statements and looking at the final result. So here's our plot that came from the statement we just executed. And if you go back and look at it, you can see that what we did, we really had two arguments to this graphing function. The first one were the edges. That is, it's a directed graph, and if you just look at it, you can probably figure out The second one is the nodes. So we said there are 5 nodes, and they get numbered sequentially unless you tell it otherwise. And so we have these 5 nodes, and then these pairs of integers in the first argument are the direction of the edges. So we've got an edge going from 1 to 2. We've got an edge going from 1 to 3, from 2 to 3, from 3 to 5. And then poor old 4 gets left out. And so 4 is disconnected. Okay, so there's a simple plot for you. The command V prints information about the vertices, and the command E, uppercase E, prints information about the edges, or the links, if you will. So if you don't embellish the call to V or E with other arguments, you just say V for the graph, it just shows you, V will show you the vertex sequence, and then E will show you the series of directions for the edges. So that's what we have there. Now, that's really the simple call. You can do a lot of other things, and if you go back and pull up the package, you know you can look up these functions that are not obvious what they do. We'll take a minute and take a look at the package and the documentation. Graph empty just simply creates an empty graph. And so what we're doing here is we're adding vertices to an empty graph, and that are letters. The names of the vertices will be letters 1 through 10, and they'll be colored red. So let's go down here and take a look. Okay, so it just randomly arranges these 10 vertices, A, B, C, D, E, F, G, 10 letters. And so let's continue to build on the same graph. Note the graph is an object. So as we do things to G, for example, here we're taking our existing plot and we're adding 10 more letters, progressing, starting with the 11th letter of the alphabet, and we're going to color them blue. So let's do that. And again, the arrangement is, unless you specify, and you can, there are a number of layouts, types of graphs that you can create, but you can see that it's arranging them more or less in a symmetrical manner. And so now we're going to add edges. And remember, we had edges in G to begin with. But what we're doing is we are going to sample from those original edges, 30 of them, and sample with replacement. We're going to make them green. So it's just kind of a random assignment of edges that we're adding to this new graph. And take a look at it. Every time you do this, of course, it'll be a little different because we are sample as a pseudo-random generator. Unless you set the seed, it will end up with a different result every time. So just random, we created these random edges. And now, so we can call again what is the vertex sequence, and it's the order of the first 20 letters of the alphabet. And the edge sequence came out more or less randomly. Let's see, did we have any self? It's very possible to have an edge that leads back to itself based on the random selection process that we used. I don't see any in this particular plot.